Let's begin. So today we'll be answering the question why the melting of the polar caps does not cause a rise in the sea levels. Well, what do I mean by this statement? Let's first understand that. I mean to say that when the ice that is stored in the polar caps in the North Pole and the South Pole respectively, when that ice melts, it does not cause a rise in the average sea level across the earth. This does not happen. The sea level remains the same. Why does that happen? More importantly, I would like to draw a basic generalization, which is that when any ice that is kept on water, when that melts, the level of the water itself does not change. Why does that happen? Well, to understand why such a phenomenon occurs, we will first need to understand the law of flotation and upthrust in fluids. So we will be doing exactly that in this video and the next video. Let's begin. So let's understand liquid pressure. What is liquid pressure? Basically, liquid pressure or fluid pressure in general is the pressure exerted by, let's say, a liquid. For this scenario, let's say the pressure exerted by the liquid itself at any point inside the liquid. To understand this a bit better, let's take the example of a bottle, and in that bottle there is water. Now the water exerts a pressure at any point inside the water itself, and that pressure is the pressure which is exerted by the water, and it's called the fluid pressure or the liquid pressure. So basically this is what liquid pressure or fluid pressure means. What is the difference between liquid and fluid? Fluid includes liquids and gases, because even gases can flow technically, but liquid means only liquids, right? So when I talk about liquid pressure, I can say water is a liquid, and the pressure exerted by water at any point in the water itself, that is the liquid pressure, right? Now I'll be saying a statement and I'll try to prove my statement. That statement is that the liquid pressure at any point inside the liquid depends upon the height from its free surface. What do I mean by free surface? Free surface means the surface that is exposed to the air. So if I take a bottle, as you can see in the picture right here, the exposed surface, the top surface, that is the free surface. And if I take any point inside the bottle, inside the water in the bottle, as you can see in the picture, I have taken a point. So that point, the distance between that point and the free surface, as you can see in the picture, that is basically the height, and that height does vary proportionally with the liquid pressure. I repeat what I said. The liquid pressure depends, the liquid pressure at any point inside the liquid depends upon the depth from its free surface. And this is a very interesting thing. And how do I prove this? How do I definitively prove that the liquid pressure at any point inside the liquid depends upon its depth from the free surface? Let's take an experiment, because those are the best ways to prove anything in physics or in science in general. So when I take a bottle and if I make two holes in the bottle, then you will see that the one that has more depth from the free surface, basically the one which is lower, the water which is splashing out from that hole will go further, and the water that splashes out from the top hole, that will go a little less distance. It might be a bit difficult to understand, but you can see in this picture right here, and I think that will make the whole thing a bit clearer. You can see that why does the water from one hole go further and the water from the another hole go a little less further? Well, it is because of liquid pressure. The liquid pressure, when it is more, the water will obviously go a greater distance, and when the liquid pressure is less, it will go a less distance. So basically, through this experiment, we can definitively prove that liquid pressure does depend upon the depth from its free surface, and as we go deeper inside the liquid pressure increases. A very good example I can give is the Mariana Trench. The Mariana Trench is obviously the deepest point inside the oceans in the earth, and it has an enormous pressure, which is why it's very difficult for humans to go down there. Nearly impossible, because the pressure inside that point at that depth, it's very high. So these are definitive ways to prove that the liquid pressure does depend upon the depth from the free surface of the liquid. So now that we have proven that liquid pressure depends upon the depth of a point inside the liquid from its free surface, we can say that a point at a greater depth experiences more liquid pressure. In this picture, I have taken a cubical solid, and we can easily see that the pressure acting on the lower surface of the cube is more than the pressure acting on the upper surface of the cube. This difference in pressure in turn causes a net force to act upon the solid in the upwards direction, acting opposite to the weight of the body obviously. It is similar to the tensional force experienced by a string. So the string experiences a tensional force, and this force, the upthrust, is similar to the tensional force in some ways. This is called the upthrust acting on the solid. Hence, upthrust is basically caused due to a difference in liquid pressure between the upper and the lower surface of the solid. So, how do we mathematically define upthrust? Let's see. So, now that we have understood that any solid that is floating inside a liquid experiences an upward force called the upthrust, now let us understand the mathematical expression for upthrust. Basically, the Archimedes principle gives us the mathematical expression for upthrust, which is the volume of the solid immersed inside the liquid times the density of the liquid times acceleration due to gravity. So when we take volume of the solid immersed as V, the density of the liquid as the Greek letter rho, and acceleration due to gravity as G, the upthrust acting on a solid which is floating in the liquid will be V rho G, where, as I said previously, V is the volume of the solid immersed, rho is the density of the liquid, and G is obviously acceleration due to gravity. This is the mathematical expression for upthrust as defined by Archimedes principle. If you are interested in knowing the derivation of this formula, you can leave a comment down below and I'll definitely try to help you out. Now, why is this important? Because later on when we'll be understanding the law of flotation, it is going to be very important, and we will be trying to draw some conclusions between solids and liquids through that. So now that we have understood the mathematical formula for upthrust of acting on a solid which is floating in the liquid, let's understand the law of flotation. The law of flotation states that the weight of a floating body is equal to the weight of the liquid displaced by its submerged part. So basically, whatever water the submerged part of this solid displaces, the weight of that water will be equal to the weight of the entire solid itself. Mathematically, we can write this as the weight of the solid is equal to the weight of the liquid displaced by its submerged part. Now the weight of the solid can be written as mass of the solid times acceleration due to gravity, because weight is mass into acceleration due to gravity. Now the weight of the liquid displaced by the submerged part of the solid can be written as mass of the liquid displaced by the submerged part of the solid times the acceleration due to gravity, as you can see here. Now going one step further, we can write that the mass of the solid, entire solid itself, times the acceleration due to gravity is the volume of the entire solid times the density of the solid times acceleration due to gravity, which will be equal to the mass of the liquid displaced by the submerged part of the solid times acceleration due to gravity, which is again equal to volume of the liquid displaced by the submerged part of the solid times the density of the liquid times acceleration due to gravity. Now, as I previously said, that the volume of the liquid displaced by the submerged part of the solid is the volume of the submerged part of the solid itself. Right, it makes sense, because the amount of the solid that's submerged in the liquid that is the amount of liquid that will be displaced. So, as you can see, I have written here, the volume of the solid times the density of the solid times acceleration due to gravity will be equal to volume of the solid immersed in the liquid times the density of the liquid times acceleration due to gravity. This is, you can say, a formula that we derive from the law of flotation. So, we learned that the volume of the solid times the density of the solid times acceleration due to gravity is equal to the volume of the submerged part of the solid times density of the liquid times acceleration due to gravity. Now from here, removing acceleration due to gravity from both the sides and transposing the terms, so transposing the terms from one side to another, we get the volume of the submerged part of the solid divided by the total volume of the solid is equal to the density of the solid divided by the density of the liquid. Let's take a step back and let me just repeat myself. Volume of the submerged part of the solid divided by the total volume of the solid will be equal to the density of the solid divided by the density of the liquid. Or as you can see in the picture right here, small v by capital V is equal to d1 by d2. Now why is this formula important? Well, this formula is important because in our next video we will be using exactly this formula to understand why when the ice in the polar caps, or any ice for that matter, when that melts in the water, why it does not cause a rise in the level of the water. We'll be using this formula to understand that in the next video. So stay tuned. Thanks for watching and do subscribe to my channel. See you in my next video.